Alright, so this is 363 on your TA. If you have a good solid background of statics, it'll help because this class is basically like 50% statics and then 50% new material. Alright, so let's start with the problem solving aspect of this course. Okay, so the first problem that you're faced with is two cylindrical rods and it's connected by a wall. They give you two forces, a 40 kilonewton force applied at, this is A, B, C. Okay, so there's a 40 kilonewton force applied at B, and then there's a 30 kilonewton force at C. Okay, and the question's asking what is the stress in each section in rod A, B, and rod B, C. Okay, so they want to know the stress in each section. And what's a stress? You guys probably just learned it. It's a force over an area, okay? So if you want to know what forces these rods are experiencing, you're going to have to draw a free body diagram of the whole thing and then each part of it. Okay, so let's draw a free body diagram. Okay, so I'm going to draw a free body diagram of both these rods. So I'm disconnecting it from the wall. Okay, so you have these two forces obviously, right? I'm just disconnecting it at A. Okay, so what do you guys expect at A? There's going to be a reaction force. Did you guys take statics like last semester or something? You guys remember? Alright, so there's a reaction force. We'll just call it, I guess, RA, whatever you want to call it. Okay, so there's a reaction force at A. Alright, so how are we going to get this force? How are we going to know what it is? We have to do something. Equilibrium. In which direction?
Y.
Y, okay, yeah. You want to sum the forces in the Y direction. Okay, so you have RA minus 40 minus 30 is equal to 0. So RA is equal to 70 kilonewtons, okay? Kilonewtons is 10 to the 3, okay? It's 10 to the 3 newtons. Okay, so RA is 70 kilonewtons. Now we want to know the forces in each rod, okay? So we're going to draw a separate free body diagram of each rod. I'll just erase this one. Actually, you know, let me draw it right here. Okay, so this is another free body diagram. So now I'm disconnecting these two rods. Okay, so these two rods are disconnected, rod AB and BC. So what forces do you expect on BC, right? The only forces is 30 kilonewtons, and it's in tension. So it's 30 kilonewtons. This is 30 kilonewtons. And there was an applied force of 40 over here. So this is 40 kilonewtons. But what else? There has to be an equal and opposite force on this rod. So this 30 has to be on this rod too. So there's also a 30 kilonewton force, right? Because it has to be in equilibrium. We discussed that this reaction force over here is 70 kilonewtons, right? So we should have 70 on this side and 70 on this side, 30 on this side, 30. So they're in static equilibrium, right? So you know the forces on rod A, B, and B, C. So now you want the stress in each section. So the stress in each section is just the force over the cross-sectional area. And these are rods, so they're cylindrical. The cross-sectional area is what? It's a circle. Yeah, it's a circle. So we want the stress. So the stress is denoted by sigma. It's a normal stress. Sigma AB is the force over the area. Well, the force it was RA, but we'll just use a number. It's 70 times 10 to the third. This is newtons over the cross-sectional area, which is pi over 4 times the diameter. They give the diameter D1 as 50 millimeters. So it's 0.05, 0.05 meters squared. Okay, so this will give you the stress. So the stress in rod AB, where is it? Okay, so the stress in rod AB is 35.7 MPa. MPa is megapascals, it's 10 to the 6. Any problems with that, or no? No problems? Problems? Alright, so now that you guys know the stress in AB, what's the stress in BC? If I want the stress in BC, it's the force over the area. But what force are we using now? This is rod BC over here. So the stress in BC is the force, which is what? It's 30 kilonewtons, so it's 30 times 10 to the 3 newtons, all over the cross-sectional area, which is pi over 4 times D2 squared. Well, D2 is 0.03 meters squared. Okay? So the stress is 42.4 MPa. Okay, so this is your solution for problem 1. Any questions? Okay. No questions? Alright, so they give you the cross-sectional area of this link right over here. This link is B, D. Let me letter all these. This is B, this is A, F. Okay, I think I got everything. Okay. Alright, so they give you an external load of 60 pounds, and they give you an angle. For part A, they say the angle is 0 degrees. So theta is equal to 0 degrees. And for part B, they say the angle is equal to 90 degrees. Okay? They want the normal stress in link DE. Okay? So we're going to have to draw a free body diagram of possibly this link, you know? and then we're going to have to know whether this link is in compression or tension, and then we could get the stress in that link. Okay, so what happens when theta is 0? You just collapse this onto the y-axis, right? It's on the negative y-axis. So we want to draw a free body diagram of this link, CEF, and also what DE is going to look like. Okay, so let's draw a free body diagram of this. Do you guys remember this from statics? It's just statics over. The only new concept is stress. Okay. Oh, and they give you the area, the cross-sectional area. They say the area of link DE is equal to, it's 1/8 of an inch times 1 inch. Okay, so it's 1/8 of an inch squared. Okay, so let's draw a free body diagram of link CEF. Okay, so you got this link over here. And now for part A, theta is equal to 0, so we collapse it onto this y-axis. Okay, so this is 60 pounds, so it's straight down, right? There's a pin here, and then there's a pin here. So what forces do you expect at C and E? You guys could just shout out if you want. This is point F. What force do you expect at C?
CX and CY.
Okay, CX and CY. That's fine. All right, so let's just draw that in CX and CY. Okay.
I have a question.
What do we?
Why is F going straight down?
Oh, because in the problem they said.
The angle is 0.
Yeah, theta is equal to 0. Okay, so yeah, the angle's So this 60-pound force is straight down, because theta is measured from the negative y-axis. If you want to think of this as x, y. All right, so you have CX, CY. First of all, before you even start labeling this free body diagram, what do you think this link is going to be if theta equals 0? Is this link going to be in tension or compression?
Compression.
It's going to be in compression, yeah. You're pulling this thing, it's going to be compressed. This link's going to be compressed. So that means this force has to be upwards, right? Because if we draw the free body diagram of the link, right, it's in compression, right? So this force has to be equal and opposite. What do you want to call this force? F-E, F-E, F-E. Okay. So this is a free body diagram of ED, right? So this is in compression, so this force has to be equal and opposite. So it's upwards. So this is our complete free body diagram. So if we sum the forces in the x direction, what do we get?
CX equals 0.
CX equals 0. So there is no CX. But that was good anyways. It's fine. You could always figure that out from equilibrium, right? And what is this? Why didn't I draw an x component? Why didn't I draw an x component in this member? What's special about this member?
It's a two-force body.
Two force member, exactly. There's no x component. It's just along the member. Okay. So, all right. So we got the complete free body diagram. Now we just need dimensions. Okay. Because we're gonna have to sum moments. So this is 4 inches. No, it's not. It's 16, right? Yeah, 16. This is 16 inches. Yeah, and this.
Oh, that's 12.
Oh no, it's 12. You're right. Whoops. Sorry about that. You're right. It's from here to here. Okay, yeah, it's 12 inches. Okay, and what about from here to here? That's 16. Okay. So this is 16 inches. Right? Okay. So now we have everything. Okay. So now what do you want to do in order to get this force? We want to know the stress in this link, so we want to get this force, right? Once we get this force, we know this force because it's equal and opposite. Then we can get the stress in this link because we know the cross-sectional area. So what would we do to get that force? Sum the yeah. So you guys know. Don't be afraid to answer. All right. So you want to sum the moments about C. All right. So let's sum the moments about C. Point C to be 0. Okay. Nothing's moving again. So you have 12 times FE, and that's plus, right? Because it's going counterclockwise. And then you have minus 16 times 60 equals 0, right? That's summing the moments about C. There's only two forces causing a moment, FE and F. Okay? So the only unknown is FE. We could solve for FE. So FE, well, I labeled it capital E. Doesn't matter. You guys know what I'm talking about. I'll just be consistent. Alright, so FE equals 80 pounds. Alright, so now that we got FE is 80 pounds, we could get the stress in this link over here. So what's the stress in link DE? So sigma DE. It doesn't matter what you label this. I'm just doing it for convention, so you know what link I'm talking about. So the stress in DE is what? Be careful the sign. Did Gupta tell you, like, if it's in tension, it's positive, the stress is positive. If it's in compression, it's negative? Did he tell you that?
Yep.
Yeah, okay. So it's negative, the force over the area. So the force is 80 pounds over the cross-sectional area. Well, they gave you the cross-sectional area. I just erased it. It was 1/8 of an inch times 1 inch. Okay, so the stress you get is minus 640 psi. Okay, be careful of the units. Okay, before it was megapascals or pascals, and this is psi. This is pounds per square inch. Okay, this is the English. That was SI. All right. So that's your answer for part A. And then for part B, they asked when theta is equal to 90 degrees, what is the stress in that link? Okay, so we have to draw a new picture, right? This no longer applies. We're doing part B now. Can I erase it? All right. Okay, so now theta equals 90 degrees. So I'm just going to draw it like this. Let me erase it. Okay, so now we want to draw a new free body diagram. I'm going to leave this and just change this so I don't have to redraw everything. So this is now to the left, it's 60 pounds. Okay, so what's going to change about this free body diagram? Nothing. Nothing's going to change. Before you didn't have a CX. CX was 0, but now you do have a CX. CX equals to 60 pounds. Okay, so the free body diagram is the same, right? So the only thing that's going to change is when you sum the moments, right? Because now we need this distance over here. We no longer need this distance of 16 inches. So we need this distance from B to A, correct? So it's 8 inches, right? No, it's 8. It's 8 inches. Okay. Yeah, from here to here is 8. Okay. So, alright, we don't need this anymore, so I'll just erase it. Okay. So now we want to know the stress in this link again, so we're going to have to sum the moments at C to get FE. Once we get FE, we can get the stress, okay? Because it's a force over there. Pretty simple. Alright, so let's sum the moments at C again to be 0, taking counterclockwise to be positive. You have 12 times FE, that's positive, and then you have minus 8 times 60 is equal to 0. So FE is equal to, now in this case it's actually half of it, so it's 40 pounds. Okay. So we got the force. Again, we're going to do the same thing. We want to get the stress in that link. So it's just the force over the area. So now the only thing that's changing, the cross-sectional area stays the same. It's not changing. So the only thing that changed is this number right here, the force. So you have 40, it's minus 40 pounds over 1/8 of an inch squared. So the stress now is just going to be half of what we had before. So it's 320 psi. This is for part B. Whoops. Any questions? No? Yeah, you have a question?
Why is it in compression?
Why is it compression? Well, think about this. If you're pulling it this way, it's still going to be in compression.
All right,
You see it? Yeah, if you still pull it this way, it's still going to be in compression. The only way it's going to be in tension is if you push it up. Or if you push it at an angle up, you know? Then the link's going to be in tension. Any other questions? That's a good question. Yeah, but you could, that's the main point. That's a good question. You know what? When you're taking this class, it's not like statics where you're like, oh, I don't have to think. I just draw CX, CY, and then just do equilibrium. You have to think. In this class, you actually have to think which direction is the force going to be. So I tried in statics to get you guys in the habit. I don't know if any of you guys took statics with me, but I tried to get you guys in the habit of drawing the right direction. Kupta was like, just draw any direction and the sign will correct itself using equilibrium, but that's not a good habit. So, okay, because you're going to need to draw the right direction for this course. Well, I mean, if you drew the wrong direction, you would still get, you know, it's supposed to be upwards in this case. But in some cases, you're not going to be so lucky. Alright, so they give you the cross-section, in this problem, they give you the cross-sectional area of this length over here. Let me label them. This is A, C. You guys recognize this as a what?
Truss.
Yeah, it's a truss. Okay. So this is H, B, D, F. Okay. Alright, so they give you the cross-sectional area of this length over here, BE. So they give you the cross-sectional area of that length because they're going to want to know what the stress is in this length. Okay? So the cross-sectional area is 5.87 inches squared. And they want you to find the normal stress in member BE. Okay, so you want to know the stress in this member BE. So we're going to have to draw a free body diagram of this whole truss, get the reaction forces. Well, maybe I should ask you guys how to do this, because you took statics. Maybe you guys aren't like familiar yet with the stresses, but you should be able to do this problem, I think. I hope. Okay. So if you wanted to find the forces in this link, what would you guys do? Just think of statics. What would you do in statics?
Find the support reaction.
Huh?
Find the support reaction. The support reaction.
Okay, yeah, yes. Of A and H, right? And then what would you do?
The moment.
No, no moments. Do you guys remember method of trusses, the joints? Method of joints where you draw each joint?
Yeah.
You guys forgot about it already. Okay, so you got it. Yes, that's good. You got to find the reaction force at A or H. I would find it at A, because if we have it at A, we could do the joint analysis of this one, this one, this one, and then we know this force, right? You could go this way, where you find this reaction, find this joint, this joint, this joint. Oh, well then you'll know this force. So either way, I mean, you can use this side or this side. It doesn't matter.
What are we looking for?
We're looking for the force in member BE. Once we have the force in that member, we could get the stress in that member. Okay? Alright, so let's draw a free body diagram of this truss. Whatever, that's okay. Okay, so which direction are the forces going to be? Up or down? If this is all loaded down, what do you think the reactions are going to be? They're going to be upwards. Okay, so you have a reaction at A, I don't know, I'll call it A, and then you have a reaction at H, and I'll call it H. Right? Normally you would have an AX, AY, right? But what does AX equal in this case? It's 0. There's no forces in the x direction. So don't even bother drawing it in. As long as you know that. If you don't feel comfortable just writing this, then put in AX, but it's just 0. So it doesn't matter. Okay, so you have, let me just call this FA so people don't get confused. FH. Okay, so those are your reaction forces, and we need these distances because we're going to have to sum the moments. 9 feet. Okay, so let's sum the moments at, I don't know, it doesn't matter. Let's sum the moments at A, just to refresh your memory. We'll sum the moments at A to get FH, and then we'll sum the forces in the Y direction to get FA. Okay? Most people would just sum the moments here, get FA, and be done with it. Okay? So let's sum the moments at A, just to refresh your memory from statics. Alright, so what do you have? You have 9 multiplied by 80. And is that positive or negative? I'm taking the moment to be counterclockwise as positive. So it's negative, yeah. So it's minus what? I did this force.
18 times B.
What?
18 times B.
Okay, 18 times 80, yep. Minus what?
27 times
27 times 80, minus, well, plus.
36 times that.
Yeah. 36 times FH, lowercase. Okay, so the only unknown obviously is the reaction force at H. So we want to solve for FH. So FH is equal to 120 kips. And this is kilopounds. Okay. Okay, so now we want to get FA. Well, you could just sum the forces in the Y direction. Picking upwards to be positive, you have FA minus 80, minus 80, minus 80, plus FH is equal to 0. So FA is equal to 120 kips. Okay, it's symmetrical. It should be equal. Kips. S. Alright, so we got the reaction force at A. Now we want to do the method of joints. We want to analyze each joint. We want to analyze A, then C, then B, and then we could get the reaction force in this, we could get the force in this member, and then we could get the stress. Okay? So, any questions up until now or no? When does this class end? So I know if I have to hurry up.
That's in like 15 minutes.
Okay, so I have to hurry up. Okay, so let me erase, let me keep this, let me erase this. Let's draw a free body diagram to 120 kips. What else do we have? Now think about this. Before we draw the forces in, think about it. So this truss is being loaded. So what direction do you think the forces, what do you think member A, B is going to be in? It's going to be what? In compression? Yeah, it's going to be in compression. And these are two force members, right? They're two force members, so it's going to be down and to the left, right? So it's going to be like this. Yeah, I know what you were saying. You're right, though. It's going to be like that at some angle. That angle is going to be, you can measure it from here. Doesn't matter, or from up here. So we have to find that angle, right? And then there's one more force, right? What do you think member AC is going to be? If you're pulling this thing, think about it. What is that going to be in compression or tension? Tension. It's going to be in tension. Okay, so you guys got it. Good. Most people can't see that for some reason. Okay, so yeah, it's going to be in tension, right? The reason why I'm drawing the arrow, this is a joint, right? And the member looks like this. I'll just draw the member really quick. It's in tension, right? So this has to be equal and opposite. That's why I drew it outwards and that's inwards for compression. Okay, so this is unknown. We don't know this force. I'll call it, let me be consecutive with my notes so I don't throw myself off. I called this FAC and this one FAB. Okay. Okay, so how are we going to get that angle? By using, we have dimensions. So, okay, so you want tan theta is equal to 12 opposite over adjacent, which is 9. So you want theta, you take the inverse tangent, so it's the arctan of 12 over 9. So that's equal to 53.1 degrees. Okay, so you have theta now. So you know this is equal to theta equals 53.1 degrees. So now we can do equilibrium, right? There's no summing moments because it's just a point. So we're just going to sum the forces, right, in the x and y direction. So what are we going to do first? Are we going to sum the forces in the x or y direction? I want to see what you guys think. You know this, right? Why? Why is right, but why? Because you know this, right? You know, you sum the forces in the y direction, you're going to get this force. Then if you sum the forces in the x direction, you could get this force, right? You can't get this force unless you get this force first. Okay? So that's why I asked you. I wanted to see if you guys were, like, knew what you were talking about. Or, because it's a 50-50 guess. It could be like, you know, but you guys know what you're talking about. Alright, so summing the forces in the y direction to be 0, taking upwards to be positive. So you have minus FAB sine of theta. I'll just leave it in terms of theta right now. We know theta is equal to 53.1. And then you have plus FA is equal to 0. Okay, these are the only two forces. This is known. This is 120 kips. This is unknown, but sine of theta is known because we know theta is equal to 53.1. So we could solve for FA. FAB. Sorry about that. We know FA. This is equal to 120 kips. Okay, so FAB is equal to 150.1 kips. Okay, so we found this. Now if you want to find FAC, I don't even know if you have to, but let's just find it. Okay, so we want to find FAC. We want to sum the forces in the x direction. Okay. So let's do that. Summing the forces in the x direction to be 0, taking the right to be positive. You have FAC, right? That's to the right. And then you have minus FAB cosine of theta is equal to 0. So FAC, which is unknown, is equal to FAB cosine of theta. And FAB we just found, it's 150. So this is equal to 150.1 kips, and theta is equal to 53.1. So FAC is equal to, did you have to restart it or no? Oh, you did, thanks. Appreciate it. Okay, so FAC is, where is that? I didn't even find it.
I don't think you need it.
Okay, so you probably don't need it. That's probably why I didn't find it. Alright, so yeah, you guys could plug and chug if you want, but I guess you don't need it. Okay, so let's do a free body diagram of this joint now, right? We have this force, okay, we know this force. This is unknown. This will be unknown in this. I think you do need it, because then you're going to have to find, well this is, no actually this is known. This is 80 and this has to be 80, so these two are unknown. Yeah, you don't need it, you're right. Okay, so keep this in mind, right? I'm going to erase it now. I should keep this free body diagram. So, okay, so free body diagram of joint B. Okay, so let's draw joint B. Joint B is here. Okay, so we drew this this one in compression. This member AB is in compression. So this has to be equal and opposite. So this is FAB. This angle over here is theta. It's the same angle, and FAB we just found to be 150.1 kips. Okay, so what other forces do you have? So you have FAB going into the joint. What do you have? What else? We're cutting it all here. So it's cut, 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 cut. So what do you have? Well, what is this going to be? In tension or compression? BC. If you're pulling down on this. In tension, yeah. So so it's going to go out, right? So this is FBC. What about this member over here, BE? Is it going to be in tension or compression? It's also going to be in tension. So this is going to be outwards. This is FBE. And then we got one more. Now, let me erase this so you can see it, sort of. This is an arrow pointing into the joint. So which direction is this going to be in? To the left or to the right? To the left, exactly. Why? Because these components are to the right. This component's to the right, and this component's to the right. So you don't even really have to think about that last one. You're going to know it has to be to the left. So this is FBD. So B. Okay. All right. So this angle is still the same as this angle, and this angle over here is the same as this angle. So all the angles are the same. So this angle's theta, right? Got that? Yeah, that's it. Okay. All right. So theta is still 53.1 degrees. All right, and this is a free body diagram of the joint. This arrow is outward. I should have drew it bigger. You guys could all see this though, right? Do you want me to redraw it now? Okay. So this is into the joint, this is out of the joint, and into the joint. Okay? So we want to do a force balance. We know this force, right? Okay, so we know this force. If we sum the forces in the x direction, we're going to have 1, 2 unknowns. If you sum the forces in the y direction, you're going to have 1, 2 unknowns. Okay, so, no, but we have to draw a free body diagram of C to get this, because we know what this is, right? Let's draw one more free body diagram. Free body diagram of joint C. Alright, you have this, right? This is, we said this was already going to be in tension, right? So it has to be equal and opposite. It's to the left. This is FAC. This is FCB. And then we got this 80-pound force. 80 kip force. So you have to have a force equal and opposite. So this is FBC. Yeah, I called it FBC right here. Okay. So if you sum the forces in the y direction, you get FBC is what? 80. Yeah, so this is 80 kips. Right? So we know this. So this is actually equal to 80 kips. I know it's kind of cluttered. That's why I was going to redraw it, but it doesn't matter. So the only unknown is this one and this one, right? So we know what could we do first? You sum the forces in the y direction. It's like just like before. We want to sum the forces in the y direction to get this force, right? That's what we're looking for. We don't have to sum the forces in the x direction because we don't care what this is. They want to know the stress in this member over here, right? If you sum the forces in the y direction, you're going to get that force. You guys agree? Okay. So I'm going to erase this and just do it here. So let's sum the forces. Summing the forces in the y direction to be 0, taking upwards to be positive. You have FAB sine of theta, which is known. You have minus 80. That's FBC. So maybe I should just put, no, whatever. You guys follow what I'm doing. All right, maybe let me call this a variable. All right. This is FBC, but this is equal to 80, right? And then you have minus FBE sine of theta, and that's it, right? It's just these three forces. 1, 2, 3. Those are only in the y direction, and this is equal to 0. Okay? So this is known. This is 150.1 kips. This is 80 kips. And theta is known, it's 53.1. So we want to find this. This is unknown. So FBE is equal to, after you guys plug and chug, you should get .1 kips. Okay. Alright, so we already discussed this is going to be in tension, right? So now we want to find the stress, so it's just the force over the area. So this is the link right here that you're looking at. It looks like this. It's in tension. This is B, and this is E. Alright, and that force happens to be 50.1 kips. 50.1 kips. Okay. Alright, so it's in tension. So we want to find the stress. So the stress is just a force over the area, but in the original problem they give you the cross-sectional area of that member. It was like 5.87 inches squared. Okay, so they give you the cross-sectional area, they want the stress, so sigma BE is equal to force over area. It's in tension, so it's positive. So it's 50.1 times 10 to the 3 pounds all over the cross-sectional area, which is 5.87 inches squared. Okay, so sigma BE is equal to 8.535 KSI. Alright, so that's just stress in the link. Am I out of time? I'll see if I can run through one more. This is quick. So just so you see shear stress, because I think you have homework on it. Any questions? No? Okay. Yeah, this is a terrible picture. Okay. I I hope you guys can see what I'm drawing because I can't see it. This is terrible, I'm sorry. Okay, so basically what you have, this is a nightmare. Let me try to draw it. One more try. Okay, I think I got it this time. Do you guys see what this is? It's like a sandwich. There's two blocks, and there's a block here and a block here. Do you guys see what I'm trying to draw? Okay, I hope so. It's pretty hard to draw this. Okay, this is 5.8 kips. Alright, so basically they're glued together. This block is glued together and they give you, there's a gap over here. This gap is just empty space, right? And they give you the dimension of that. They say W is equal to 1/4 of an inch. And the other dimension, they give you the width of this. So they say B, they call it B, is 4 inches. Okay, and then you have this length over here, L, which is unknown. And what they give you in this problem, they give you the shear stress should not exceed 120 psi. Okay, so they want to know, they want you to find the length which this glue will hold this thing together when you're pulling these two blocks in tension. Okay, so basically what's going to happen is it's going to try to shear off, right? Do you guys understand what's happening? So you're not dealing with normal stress anymore. You're dealing with shear stress because it's parallel to the surface. It's no longer perpendicular. Okay. So tau is for shear stress. All right. So they want you to find what this length is, right? And they give you these dimensions. So tau has the same concept. It's still force over area, but it's a different area you're talking about, right? This is the area you're considering this time. So it's not the cross-sectional area, because the cross-sectional area is this, right? You're not considering this area. You're considering this area where the glue is. You guys follow? Stomach's growling. Alright, so tau is equal to the force over area. Well, the force is just P. It's loaded here. P is equal to 5.8 kips. Okay? So it's equal to P over A, so we have to solve for A because the only unknown is L. So what is A? It's this area and this area. So what is that? Someone give it to me quick. So it's A is equal to P over tau. So A is equal to what? What is A? It's L minus W times B, right? That's the area. So it's L minus W times B is equal to P over tau. This is known, this is known. This is the only thing that's unknown, this is known. You can solve for L, move this stuff over. So it's P over tau B, and then plus W, right? That's just algebra. You guys could all do that. So this is equal to, L is equal to 12.3 inches. Okay, I guess I'm out of time. I'll upload this. You can look at it on Blackboard. Thank you. My stomach